You ever write a line of code and just wonder what's really happening? How do our nice, clean commands actually get turned into something a piece of silicon can understand? Well, today we're going to dive in and pull back the curtain on that whole journey from your screen right down to the processor's core. When you get right down to it, this is what a computer program looks like. It's just a long, wild sequence of ones and zeros. This is machine code. It's the native language of your processor. And yeah, to us, it looks like total gibberish. But hidden inside that chaos is the precise set of instructions that brings all our software to life. That's the million-dollar question, right? How do we possibly bridge the gap between how we think in words and logic and how a computer thinks in pure electricity? Well, that translation process is exactly what we're going to unpack. To really get this, we first have to understand the two languages that are in the conversation. On one side, you've got us, the humans, and on the other, you've got the machine. And this slide just nails the difference. It's all about something called abstraction. See, we write in these high-level languages, like Python, where one simple command makes perfect sense to us. But that one line of code, it might actually explode into 10, 20, or even more little steps for the processor, all written in that low-level machine code. We're basically hiding all the messy details to make our lives easier. Okay, so we have our awesome high-level languages, but the processor only gets ones and zeros. So how do we connect the two? We need a translator. We need a bridge to get from our world into the hardware's world. And this right here is a brilliant picture of that bridge. It's called assembly language. Instead of trying to remember that a crazy string of binary means add two numbers, we can just write a simple, easy-to-remember command like add. Think of assembly as the human-readable version of machine code. Assembly is built on these little things called mnemonics. And really, that's just a fancy word for a memory aid. You use them all the time without even thinking about it. When you text L8R for later or GR8 for great, that's a mnemonic. In assembly, MOV stands for move, AD means add, and sub is for subtract. They just make the code make sense at a glance. So how does this all fit together? Let's walk through the whole process. First, you write your program in assembly language, which is really just a plain text file. Then, a tool called an assembler takes that text and converts it into an object file. That's the raw machine code. But it's not quite a program yet. It's missing a start and an end. That's where the linker comes in. It's the final piece of the puzzle that stitches everything together and creates the final runnable program. Now, here's a key thing to remember. Not all processors speak the exact same dialect of machine code. We're going to focus a bit on the philosophy behind ARM chips, the kind you'd find in a Raspberry Pi or even your smartphone. And this is a super important point. Every type of processor has its own unique set of commands, which we call an instruction set. This means a program that's been written and compiled for your Intel desktop computer will not just magically run on an ARM-based phone. It's like they're speaking two completely different languages. The R in ARM actually stands for RISC, which means Reduced Instruction Set Computing. The whole idea here is simplicity. Instead of having hundreds of really complicated instructions, the RISC philosophy says, let's have a much smaller set of instructions, but let's make each one do one simple thing incredibly fast. It's the total opposite of older designs, which we call CISC for Complex Instruction Set Computing. Think of it this way. A CISC processor might have one giant command for a complex task. A RISC processor breaks that same task down into 3 or 4 tiny lightning-fast steps. And this simple approach has some huge advantages. With fewer instructions to learn, the processor itself can be simpler. Because each instruction is so simple and clear, the performance is just faster. And that combination makes RISC chips like ARM super powerful, but also incredibly energy efficient, which is exactly why they are absolutely perfect for our phones, tablets, and all sorts of other compact gadgets. All right, we've talked a lot about machine code. Now let's get our hands dirty. Let's really dig in and start decoding the ones and zeros themselves. Okay, thinking in binary feels a little weird at first, but I promise you already understand the basic concept. Think about the number 2,934. The 2 is worth way more than the 4, right? That's because of its position. Well, binary is the exact same idea. A bit's position gives it a weight. But instead of powers of 10, like we use, it uses powers of 2. The first position is worth 1, the next is worth 2, then 4, then 8, and it just keeps doubling. But let's be honest, staring at long strings of ones and zeros is a total nightmare for us humans. And that is why hexadecimal, or hex, is so important. It's a base 16 system. And here's the magic trick. 4 binary bits map perfectly to one single hex digit. This means we can represent a whole byte, that's 8 bits, with just 2 characters. It's the compact, readable shorthand that programmers use absolutely everywhere. Okay, so this has been a fun trip down the rabbit hole, but why does any of this low-level stuff actually matter? How does this make you a better programmer out in the real world?
Because working at this level gives you some serious power. First off, programs written directly in machine code just run faster. There's no translation step needed. Second, you get direct, unfiltered control over the hardware. But maybe most important of all, it teaches you what's really going on under the hood, and that makes you a smarter, more effective programmer, no matter what language you're using.
Here's a perfect real-world example of a low-level limitation. A 32-bit system can only see or address about 4 gigabytes of memory. And that's not a software choice. That is a hard physical limit of the architecture, based purely on the number of bits it has to work with. Remember that number, roughly 4 billion. But then we jumped to 64-bit. And the change is, well, it's staggering. The theoretical memory limit isn't just double, it's 18 quintillion bytes. To even try to wrap your head around that number, if each one of those bytes was a single grain of sand, 18 quintillion grains would be enough to cover the entire Sahara Desert. That is the insane leap in scale we're talking about. And all of this brings us back to one of the oldest, geekiest jokes in the tech world. If you didn't get it before, you definitely will now. The number 10 in binary isn't 10, it's the number 2. You've got a 1 in the 2's column and a 0 in the 1's column. So congratulations! By understanding this journey from code to the computer, you're not just a better programmer, you're officially in on the joke. But more than that, you're starting to see the beautiful simplicity that's hiding under all the complexity of modern computing. And that right there is a really powerful way to see the world.